Hello. I will report and present the Gemini project. We'll talk about our aims to actually make our data fair and how we plan to do it. And I will also talk about the medical information platform presented to you. The Gemini project is a European project funded by the European Commission, and it aims at delivering a digital twin in stroke. What is a digital twin in health is actually a model, a validated model, which is covering multiple organs and multiple scales. It's a computational model, and the aim is to improve the treatment of stroke and reduce the burden of the disease. So the principal investigator is Henk Markering from Amsterdam, and the leading team is composed of Alphonse Utstra, it's composed of Charles Majois, and Sven Hirsch and myself for everything which is regarding aneurysms. The project started the 1st of December 2023 and is going to end end of 29. And this is a summary of the project. What I think is very important is that actually it's a technology push, and then it's a clinical pull system where there's an iterative feedback. So it's something which is going to circulate through cycles, and it's integrating knowledge and data. So the integration of knowledge is actually the pathophysiological models, which are multi-scale and multi-organ, that integrates our knowledge about interactions of phenomena and things. And then we have diseases. We have two diseases. We have ischemic stroke and hemorrhagic stroke. And in those diseases, we are looking at different phases of the disease. We are looking at etiology and the ways to prevent the disease. We're looking at the treatments of the disease, and we're looking also at the progression of the disease and the long-term follow-up to actually quantify the burden of the disease. And once we have generated an overall stroke, or what we call a generic stroke model of those two diseases, then we want to actually refine it, to be personalizing it, to actually be fitting each individual as much as possible. And that's going to be a very iterative process. And finally, those models will be validated by proof of concept in studies and even a clinical trial. There's one important aspect here, which is harmonization and quality assurance and verification of the data. So that's the core of the project, is also to improve technologically regarding information technologies, to be improving the efficiency of the system. So the infrastructure we're starting with is actually an infrastructure that guarantees data protection, good clinical practice, and stores and protect data and deliver services to doctors, to citizens, as well as patients, and maybe also the science community and the politicians. So what we have is we're working on the aneurysm protocol regarding the aneurysms. The aneurysm protocol is actually on clinicaltrial.gov. It's accessible. You can look at it. You can upload the informed consents. You can upload the study protocol, and you can even ask us to improve the protocol. So it's something which is not fixed. It's possible to get it progressing. We then have a link to the aneurysm databank. There's a paper describing the infrastructure and the concepts behind the aneurysm databank. And then you can actually access the data through a portal, through a web portal, and you can access images through another portal, and both things are linked. So actually, it's kind of a PACS system for scientific projects, and it's called KEOPS. And all the data is fully de-identified. On the other side, legally, we are managing all the data transfer agreements, and we have a template of a data transfer agreement, and this can be project study specific or can be generic. So we're managing all that. And finally, we're involved, and we are really implementing recommendations regarding common data elements. We're working on an ontology, on an OWL file, and we have a representation of data in a database, and we're working, as I will talk about the semantic web technologies to actually get it improved. So the current limitation are that the field is profoundly biased by framing bias. We only have access to 3.3% of the patients, and we have access to the worst patients, meaning the one that suffered of an intracranial hemorrhage, that suffered from a bleed of a subarachnoid hemorrhage. And there's only a very small minority of the patients which are diagnosed incidentally with aneurysms that we know about. And the vast majority of those people are running around without noticing they have an aneurysm, and we have no idea of what this population is. So that's something we have to take into account and something we have to work on. The other thing is that we so far made the assumption that all the data, all the factors we are studying are independent, and our models are based on the assumptions that things are independent, and actually they are not. So we have to take into account those interdependencies. And finally, what we also have is that we don't have access to the principal factors. We only have access to surrogate factors. So we actually have to interpolate, or we have to impute the effect on principal factors of what we can assess. And that's something we can benefit of knowledge, we can benefit of models, and that's what we're going to work on. The other current limitation is that we lack of granularity. We have a lot of binary factors, we have a lot of categorical factors, and we actually like to have some more continuous data. But this is resource intensive, and we need to provide the services to help people to have access to those continuous data. Finally, or not finally, I mean that's a very important aspect, is that we are facing a lot of heterogeneity on the clinical data, and we use a lot of documents, PDFs. We have Excel files. Now we actually move to CSV and SQL files. And what we'd like to go is move now towards RDF, so resource defined frameworks, and eventually go to the linked open data in health. And the other thing which is extremely important, and that's one of the reasons why we're working with the ISGC, and that I think the ISG is very sensitive of, is power. Power needs numbers. Numbers needs a lot of centers. It means that if we want to do good science on the topic and on any health topic, we actually need to have a certain amount of centers, meaning that we need to synchronize our practices globally over different centers, which is far from easy. So I think that the minimum is to have a network of approximately 40 centers collaborating together to be raising the numbers and actually show us relevant results and observations. So semantic web technology is something which we talk about at the W3C for quite a while. It's actually identifying everything with a number, to make it very simple. So you can actually characterize all the letters with a number, you can characterize all the words with the numbers, and you can characterize all the interactions between verbs with numbers, so a computer can understand actually language. And so there is a subject, there is a relation between a subject and an object, which is a verb. So it's just applying what we do when we speak, but do it in a way, a very formal way that allows then computers to understand what we do. And then that brings graphs, that brings relations, and allows to actually see a lot of things. And this, we need to do it in a secured space, so we actually endorse the recommendation of the health data space provided by the European Commission. So that space actually is now moving towards what we call the medical information platform, which is actually within that secured space a tool which is like a GitHub. So it allows each researcher or each participant to have his own workspace to collaborate with others like we do in GitHub, and actually to have access to data and access to resources, meaning accesses to softwares or computation power. And so the medical information is actually led by the eBrains project, which is coming from the Human Brain project, and it's networking across Europe, and it's progressing very nicely. And we should have a release of the first prototype by the end of this year. And finally, if we code models, it's very important we are interoperable. That's the reason why we follow the VNV40, and we recommend the community to follow the verification and validation protocols printed by the ASME, which are the VNV40. So how does the data look? So we have nodes and we have edges, so we represent that in graphs. And each graph represents here the distributions of patients we can see with those different dimensions. And we can get that interactive, so you can fix one parameter and you can see how it has an impact on the distributions of all the other parameters. And here you can see that if you change male and female, you see that it changes the location of aneurysms, it changes the smoking pattern, and it has some effect on the rupture risk and rupture status. So what we're doing now is we're, from that very simple model you saw already a few times, we are actually adding vasospasm data, we're adding ischemic neurological deficits, information, disability, and mortality that are in the new outcome assessments. And regarding the modifiable factor, we're introducing intervention because it actually modifies completely our distribution of patients. So it's a very important information to add to actually have a good model of the disease and a good epidemiology of the disease. And finally, what we try to replace categorical variable with more continuous variable like aneurysm shape. And we're also adding some genetic markers coming from that team. And we're actually now moving also from patient level data sets to an aneurysm level data set. So we are really seeking for aneurysms level, so actually to have the information about all the aneurysms of a patient in the initial conditions and over follow-up, meaning that we're going to have a unique identifier for every aneurysm.